Assalamu alaikum wa rahmatullahi wa barakatuh. Ramadan Kareem and welcome back to Cyber Night Season 3. Today we have two very special guests with us, Mr. Naveen Bharadwaj, Chief Growth Officer at Cyber Solutions, and Mr. Eric K. Today Mr. Eric K will be talking to us and enlightening us, and we hope to learn very much from him today. Mr. Eric K, welcome to Cyber Nights. We're very glad to have you here. Certainly your background is admired and appreciated by many and is very well known. But first, we would like you to enlighten us about yourself and what you'll be talking about today. I'd like to hand the mic to you guys and hope to learn very much. Thank you.
Great. Thank you so much, Hamad.
Thank you, guys.
Go ahead, Naveen.
Thank you, Eric. Ramadan Kareem to everyone. Thanks for the wonderful introduction. I don't want to steal the limelight from Eric because it's all about Eric and an amazing topic that he has aligned for us today. Eric is going to talk to us and all our audience about protecting their networks and data from whatever threat awaits. This is extremely interesting because the nature of cyber risks and the number of cyber attacks in our region particularly has always been on the rise. So we'd love to hear from Eric on what types of threats awaits there and the possible solutions that we have. So Eric, welcome to Cyber Nights.
Well, thank you for having me. It's an honor to be able to present and I think share some knowledge, which we like to do. And I have a long background, as you say, in working with disruptive technologies and trying to basically make the cyber community a safer space. And that's really what my career goals have always been. So happy to contribute in the region to that and some awareness of some things that maybe people haven't considered when it comes to network security. So looking forward to expanding on that topic today.
Fantastic. And that's also beautifully aligned with the partnership and the collaboration that Spire Solutions has with Quantum Exchange, as well as with the Saudi Federation for Cybersecurity Programming and Drones, in enabling cybersecurity, in enhancing cybersecurity, cyber resilience, data privacy, data security, and so much more that we're all here to do together. Eric, let's jump straight into today's session, right? In your opinion, what's the current state of networks and data threat landscape, current state of encryption, and what do you think are the different types of challenges that we all need to be aware of?
Yeah, so that's a great question. I think one thing we have to realize is that the way we encrypt networks today, the public key encryption that we use to protect everything from our phones going to our Gmail to network routers that negotiate keys to share over a VPN, for example, is based on technology that was created in 1976. And as we say in the cyber community, show me another security technology that we've been using for 45 years. And the fact is there really isn't one. And so, that's really come under threat from a number of avenues. And I think as we move to things like cloud computing and distributed networks, SD-WAN, we're going to start to see some of the weaknesses in that architecture really become impactful. And part of what we're trying to do at Quantum Exchange is address those weaknesses so that we can move forward and have data security and privacy, which is obviously very important.
Great. So what I'm hearing from you is we are still dependent on legacy technologies. We are still dependent on legacy techniques. You talked about 45 years plus. So how often do we come across organizations that are using technology or techniques that are 45 years old? Very rare. But then why are we dependent on that for addressing some aspects of cybersecurity? So how do we solve it, Eric? What's your take on the approach that we all need to take, regardless of the type of industries or regardless of the geographies that we are from? How do we approach it, and what are the solutions that you propose or that you bring to the table?
Yeah, so what we like to say is I think there's a lot of attention on what technology can we use to solve the problem. And, is there a new algorithm? Is there a new special technology? And what we're trying to do is educate people to understand that we think that this is an architecture problem first and foremost. And if you can fix the architecture, then you can do really good things from a technology perspective. But if you don't fix the architecture, then the technology is more of a band-aid than a cure. And so that's really what we like to talk about when people think about this problem. So we kind of want to change the mindset a little bit. And that's really what I'm going to talk about today. It's not even as much product related as problem related, so people understand how to address the problem.
Fantastic. So we're all eager to see what's the architectural change that you're proposing. We're also eager to see how you suggest that we solve some of the problems that you talked about. So Eric, please walk us through all of that.
Well, thank you. So let me share my screen and we'll walk through a pretty quick slide deck that talks about the problem, and just let me know when that comes up and we can see it.
We can see it.
Perfect. So, protecting your networks and data from whatever threat awaits, what we're trying to get people to understand is there are current threats that you have to deal with, and there are future threats that are coming or may already be here that people haven't really thought about. And you need to take all of these into account when you start thinking about network security. First, Ramadan Kareem, we know this is being shown during Ramadan, so we would like to acknowledge that. Really quick background on the company. Quantum Exchange was started, the research actually started years before we got our funding, but it was started in a government research and development facility and then taken and productized in 2018. And we were really here to solve a very specific problem of quantum computing going to break future encryption. And we were, very much forward thinking at this point. And what we realized as we started walking through these problems and really analyzing, why this quantum computing was going to be a challenge and what we were going to have to do to address it, that this wasn't a technology problem. It wasn't a it wasn't an issue that something was weak and it had to be fixed in a technology perspective. It turned out that it was an architecture problem that needed to be solved, and that addressed not just a future problem of quantum computing, which that future has gotten closer in the 4 years since we were founded, but also just problems that are happening today that people need to understand, and that are getting made worse by certain trends like moving to the cloud. So we'll talk about that in detail today, what those problems are. So as I mentioned, we're using some technology that's pretty old, right? Decades old for creating, distributing, and managing keys on endpoints. And that means phones, laptops, applications, routers, firewalls. Those methods were created, Diffie-Hellman key exchange, and with Diffie is an advisor to Quantum Exchange. That was created in 1976, October of 76, so it just had its 45th birthday. And one of the challenges with that solution, which has enabled all of the internet. So, we're grateful to with Diffie and Martin Hellman for creating this, but one of the challenges has been that it was developed when the network architecture was extremely different. And what I mean by that is that when this was created, if I wanted to go and create a network connection with Naveen, what I would have to do is first call the telephone company and have a digital network line, a T1 line, and typically installed between our locations so we could communicate with a network. This idea of connecting a laptop to an airport Wi-Fi hotspot and then talking to any other computer in the world, that did not exist, in part because they hadn't invented this Diffie-Hellman key exchange yet. And so it made sense at the time that you would have to generate a key on the endpoint, because you only had two endpoints talking to each other, and then negotiate that key across the endpoints, and then use it to encrypt data, and then send data over that tunnel, because you had one network connection. And it turns out that creates some really big problems, which I'll get into. And the number one is that you have a network where you could have a man in the middle, because it's a single network connection. The other challenge we're seeing is that in order to address some of these threats, people are starting to use pre-shared keys, meaning you manually input a key into both locations, and then that is used. And so there's no key distribution, which is good. But the problem there is that there's a lack of rotation. You see this a lot in military applications, for example. So you'll have somebody input a key and then it can't get rotated because it's hard to get somebody out there to do it, and you have to turn the network off to do it. It's disruptive. And so that's a problem, but also that user now knows the key. So there's a single entity, or if there's two people doing it, they will have a problem in that each person now knows the key, which isn't secure, right? That's not zero trust. That's I have to trust these two people. And rekeying is hard, like I said, and they tend not to get rotated because it's expensive to do. So the next challenge is weak entropy. And this is really being exacerbated by the fact that we're moving to the cloud. And weak entropy means that if I have two devices that are very similar and they both generate keys, because they're working with basically the same set of random bits that they can generate. And in the cloud, that's very tight. The machines are made, the virtual machines are made very small. And so they have a very limited, what they call entropy pool. And it's proven now, the research projects have been done, that if you have 1,000 Amazon instances and they generate, 1 million keys each, some of them are going to generate the same key. If I can generate the same key that you generate, I can read all the data that you encrypted with that key. So it's a problem. There are also other issues with random number generators on phones, on laptops, on physical devices, even security appliances, so routers and firewalls. It turns out that some of these random number generators, you can predict what the next number is going to be. And so that's a challenge. So weak entropy means we're going to have keys that aren't secure and that are duplicatable, which is not good. And then algorithms that we have today are vulnerable to quantum computing, and they're going to be melted. So all the public key algorithms, RSA, ECC, will go and be useless, or as the US likes to say, NIST likes to say, unsuitable for use as a security product. And then lastly, why haven't we made changes? Well, because implementation is hard. Changing cryptography is really hard. You have to take networks down. It's very disruptive to business, and changes can take years. We still have people using TLS 1.0, even though it's known to be vulnerable, when they should be on 1.2. People are using old symmetric key algorithms like triple DES because they can't move to AES. So it's very hard for people to move from one encryption solution to another. And we think that that's a challenge that needs to do what's called National Security Memorandum 8. So you can look it up online. And really, it's about improving in a number of ways cybersecurity and network security. And one of the components of that memorandum is a mandate that the U.S. government, particular components of the government, are going to have to move to quantum safe encryption within the next 180 days. Which is a very short time. So it is not going to happen. There are a lot of organizations that will apply for an extension, a waiver. But once the government makes these mandates, you will see this trickle down to first other global governments. There's no question everyone is looking at this with a lot of interest. There's a reason that this has been mandated. So people are saying, hey, if the threat is that serious, we ought to be thinking about it. So it's going to spread, and it will spread to commercial sectors for sure. This has always happened. The other problem is that there's only one algorithm you can use today that's quantum safe, and that's AES, the Advanced Encryption Standard, with pre-shared keys. So we have that key knowledge and key rotation problem that I mentioned. The U.S. National Institute of Standards and Technology has had an open process to solicit public comments and public algorithms to have these new, what are called quantum safe algorithms. So they're coming. This process started in 2016, and they are in the final round of analysis where they're going to announce the winners, if you will, that are going to be approved for use. But they have warned that organizations may have to change these algorithms more than once. So you will not be able to say, oh, we're going to use IBM crystals because this has been approved by NIST. And by the way, that hasn't been approved yet. I'm just using that as an example. But we're going to use this algorithm, and we are going to deploy it, and then done. No, you're probably going to have to change the implementation of that algorithm or switch to a new one. And I'll talk about some reasons why we are concerned about that more than once. So you're going to have to do this over and over. And the problem is just changing one takes years. So imagine having to change 3 or 4 to organizations. That's going to be very disruptive, and that's a problem we need to solve. So government mandates, just general people understanding that there are problems here. We're going to see a huge cryptographic migration, and it'll be the largest in human history. We're going to take all of the encryption we've been using for the past 45 years and redo it. And what people are really failing to realize, we believe, is that the keys are generated on the endpoints and travel together with the data because it was an architecture derived in 1976. And that creates the opportunity for a man in the middle. By attacking one single network connection, and in fact, one session, you have access to the key that is negotiated, and all the data that is protected by that key. So you can store data now to decrypt later, or you can do a man in the middle. If you can break the key, you can do damage. So imagine, to use an example, if you had an Aramco refinery that was connected with a fiber optic network, and I could tap in the middle of that and change my management information so that I was using 9,000 times the gas pressure, I might be able to blow something up, right? And it would be undetectable, which is the other problem. So the future for this, what people are proposing is a choice. You either go to some new NIST algorithm or some other algorithm, other governments are proposing algorithms, and go to that and use a math-based approach. It's using harder math that computers, quantum computers and others can't break, or you take a physics-based approach with something called QKD distances. Like 100 kilometers or less is the limit that you can send these keys. And it's theoretically unbreakable, although there have been some attacks against it, but it's also mutually exclusive to post-quantum cryptography. And I think that's a challenge that people have to understand, is that it also isn't good to make people make a choice, because if you choose the wrong one, then your data is exposed, you have to redo it. So that's a challenge that we want to address. So I mentioned NIST, I mentioned this process. It's a very open process. Anyone in the world can comment on these algorithms. You can review the algorithms. In fact, this open crowdsourcing of this analysis has been great, because the algorithms were published, or they asked for algorithms in 2016. They were analyzed by the global community and whittled down, and many were broken by cryptographers and just general hackers, which is great, because you want secure algorithms. And they're now down to what we call finalists, where they're going to have, out of a pool of 3 or 4, they'll pick 1 or 2, and that's what we'll use. Well, in 2022, again this year, one of the finalists for what's called digital signature algorithm was broken, and this was the rainbow algorithm. And it was broken by a gentleman who did it with a regular laptop, not a supercomputer, in 53 hours. And it was broken so badly because he could actually not just break the signature, he could sign stuff as that person, so he could do what's called impersonation or forgery. NIST has now said is not deemed suitable for use, which is the nice way of saying this is broken and it's terrible. So the problem is that that was the most peer-reviewed digital signature algorithm, meaning more people had looked at that, more people had reviewed it and tried to break it than sort of anything else, because it had been around since 2005. So what that tells us is we are going to find breaks in these algorithms that no one has foreseen yet, because they're actually still fairly new. And that's why we have to expect that we're going to change multiple algorithms over time, and it's going to take us, NIST says it's going to take us another decade to get these algorithms deployed. Meanwhile, potentially our data is at risk during that decade, which again is not acceptable. So because of these algorithms probably getting broken and implementations getting changed, we're going to have to do this multiple times. And new algorithms will also come and be approved, and NIST has said this will happen, and other governments are going to request that algorithms be used. And so you're going to have to make these changes, and we have to be agile to make these changes. Also, new technologies will come along, like being able to deliver quantum bits between 2 locations. You need to implement that as well. You need to not be tied to like a mathematics-based approach if there's a better one that comes along. We believe at Quantum Exchange that key generation, meaning when I create a key on an endpoint like a phone or a router, that's the next area for mandated improvement. You can't have keys that somebody can guess or figure out what the next key generated would be. In other words, they can't be deterministic. And so that's going to be something that's important, because the new set of computers is going to do some of those things really well, this guessing game. And these changes are going to be very expensive to implement. It's going to require you to take networks down. And if you stay with the same architecture we have, the cost of change is going to be very high. And if cost is high, that means it doesn't get done, which means we don't have the security we need. So what we need to address the threat is several things. One, we're going to need to start generating better random numbers for encryption keys. And one of the ways to do that is use quantum physics to generate numbers that are not guessable, they're not deterministic. And so generating quantum random on-demand symmetric keys is going to be very important. And you're going to need to be able to deliver those keys to every endpoint. So an IoT device can't generate a quantum random number, but if you could deliver a quantum random number to it as a key, that would be very helpful. The second thing is that we need to get off of the architecture where the keys are generated and distributed over the same data network. And so in our model, you generate a key, a secondary key, and you distribute it over a separate network so that it can't be tapped. You want to get rid of the man in the middle opportunity, and that's really important. You need to be able to deliver these keys over any network. So as I mentioned, QKD is a great technology, but requires either fiber optic or a line of sight laser. Well, that doesn't work for phones and tanks and trains and boats and airplanes. So you need to be able to deliver over any network, and that's something that really needs to be developed and created. And lastly, you need to be able to upgrade and change algorithms and change technologies without taking the data networks down. And so how do you do this without being disruptive? And really what this comes down to is we're going to have to get away from the current architecture we have of generating and distributing keys between endpoints directly to a key distribution network architecture to secure this. So the time is now to change the architecture. We really want to separate key generation and distribution from the endpoints that generate the data. That's really not what they're good at. What endpoints need is they need to be delivered a symmetric key, because symmetric key encryption is still safe from quantum computing as far as we know today. They need a symmetric key delivered so they can encrypt data between tunnels. That's it. They shouldn't be generating keys, distributing keys. That's not what they're good at. We think for the start, people should use what are called pre-shared keys that are quantum generated, but also try to use more than one key. Think of models like multi-factor authentication, where if you go to your bank and log in on your laptop, you can see your account balance, you can look at certain things. But if you want to send money to somebody like me, especially if you've never sent money to them before, you get a token sent to your phone, because that's an out-of-band separate communication that is not tied to your current laptop connection. And so what it does is it helps make sure that you are who you say you are and are approving this transaction. So think of that for keys as well. We should have not just one key, but two. It should be sent out of band from any other keys, so that there's no single place where an attacker can look to get access. Make the technology and the architecture that you're deploying technology agnostic. So you want to be able to deploy something like post-quantum cryptographic algorithms, PQC, but you also want to be able to move to something like QKD, or use both together so you can get the best of both worlds if you want. We believe that multiple entropy sources, key generation sources, need to be used for key generation, again, because it makes it less likely that you can determine what the next key would be, and make that upgradable. So that's going to be a challenge if you try to do that on every endpoint, right? If you can build an architecture that does this, and does it at the architecture level and not at the endpoint level, it will make it so that you can allow more frequent changes to the key distribution architecture without taking the data networks down. That means you don't disrupt the mission or the business, and that means it'll get done, right? If I can lower the cost of change, both from a business perspective and just an overall cost perspective, then things will get done. And I'll use an example. I came out of the world where when we were first developing web applications, every web application had a username and password associated with it. You actually built it into the web app. And if you had to change a user ID or change a password or change a password policy or delete a user, you literally had to go in every application and do it. So if I want to change the password policy to be something that required a number and a letter, for example, I would have to do that in every application. And so what we realized is if you can do centralized user authentication and access management, you can change it in one place, delete the user, change your password, change the user ID, and it affects all the applications. And that's the way we want to start thinking about key distribution. This is not an endpoint security problem. It's an enterprise security problem that needs an enterprise solution. So I'll talk a little bit about some use cases here. So imagine I have in Riyadh, I have a headquarters building with a branch office and a data center. And then in Jeddah, I have another data center and some other offices. And I have a link between them that is over the ground. And so you're talking around 1,000 kilometers, I believe. And so over that link, if I am sending data over a fiber optic network, which is pretty typical now, somebody could tap that network and be reading and copying my data or potentially changing it. And so I'm concerned about that. And I want to prevent this man in the middle opportunity. So in this instance, what you would do is you would have a key generation and distribution architecture where the keys are generated and delivered over a separate network from the data. And so as you see between the two data centers here, I have keys that are going up via satellite link because I might have a satellite backup network. And so the keys get delivered over a satellite link, and that's a secondary key that is used to encrypt the tunnel that is delivered here. And it's a secondary key because each of the ground stations also has what we call a pre-shared key, where somebody's put that in, but it's not the key alone. That key alone isn't used to encrypt data. It's always mixed with the key that is delivered over the satellite. And this solves two problems. One, you can't have a man in the middle anymore because there's two middles. So they'd have to try to get both. And the other problem is that now the person who entered the key at the data centers to encrypt the data no longer has all the information needed to read that data. And so it's really important to start thinking about architectures that address multiple problems. Lastly, if I need to change the algorithm now that's used to secure this link, I can do that. If I can do it quickly, within the time it takes me to rotate my keys, which might be once a day or maybe once an hour at the earliest. If I can do that very quickly, if I can change this here quickly, I can do it without taking my data networks down, or I can let my data networks continue to use a previous key until I get the new system up and running. And so it gives you some flexibility and the ability to adapt and change without impacting the data network. And we think that's also very, very important from an architecture standpoint. And this is something that a product that we deliver, FiOTX, can provide to organizations. So one more use case, which we think is a good illustration of showing the mix of technologies that you expect to see in large enterprises. And that is, I've got fiber optic networks connecting data centers. Some are cross-border, perhaps. I might have something going from, Qatar to Bahrain or from KSA to UAE. We don't know. It could, you have a partner over there that you're working with. And so the idea is that even on these cross-border networks, you want to protect the data and send keys over a separate method. And so here's a distributed network where the keys are routed over a completely separate path from the data, and that allows you to make all the changes that you need to the key distribution infrastructure without ever impacting the data at either end, and that's going to be very important. And so here I'm mixing, for the key delivery network, I'm mixing internet, 5G, satellite, whatever the technology is, we are going to be able to adapt to that as long as I have a network to deliver keys over. And that's important from a flexibility standpoint because we're moving to 5G and some of these other technologies. You can't be bound to fiber optic only, for example. So that's it for the presentation. I don't have any more slides. Naveem, I don't know if there's questions that people have that we want to answer, but I'm happy to take those, and I'll stop the share here so we can there we go.
Firstly, thank you for that fantastic presentation and walking us through some new areas that most of us might not be very aware of. I have a few questions for you, Eric. It's interesting to see the paradigm shift, and it's also interesting to see how a new approach is necessary, not a nice to have, but a must have right away. Are there any network restrictions to a solution like the one that we just saw?
Well, the only restriction so far is that you have to have TCP/IP, and you need to be able to support both. So our solution supports TCP/IP v4 and v6. So as long as you have that connection, even if it has a lot of latency, we can work and deliver keys. And we've done a lot with our solution to, for instance, when you deliver via satellite, there's very often, can be several seconds of latency. And the encryption entities that are using keys can't tolerate that. They want a key now. And so part of the trick in the infrastructure is to build it so that when you deliver a key, it's retrievable by both parties at once. And that's one of the things that we do to make sure that latency isn't an issue. So there really aren't any network restrictions beyond needing TCP/IP v4 or v6.
Brilliant. Also, now we are trying to address one problem, which is move away from legacy technologies and techniques and apply something new. What happens once the region or once companies start implementing what you showed, and then there's a new Star Trek type new technology comes in? So will this become obsolete? Will all the efforts, the investment, the energy that has gone into phasing out the old, bringing in the new, will need to be repeated again?
Yeah, that's a great question. You mentioned Star Trek, so there actually is something that people are developing that is very Star Trek-like. It's called the teleportation of qubits, and the idea is you could teleport photons to two locations that are entangled. And if you make changes to one, in other words, if you code a key into one, even though they're not connected by any network or any physical connection of any kind, the ones on the other side will generate the same key magically. It's super spooky and very Star Trek-y. So that may happen. We may see that, and that would be an awesome technology. The problem is it's not ever going to be on your telephone, right? Because your phone would have to operate at minus 40 degrees centigrade, which is very cold. So that's not going to happen. So you still need a key delivery infrastructure to do that. And what we believe is that if you take an architecture like we have, which is to separate key generation and distribution, it's much easier to integrate those technologies. And in fact, for a large U.S. carrier, a telephone provider, we have done that. We actually started with post-quantum cryptography to secure parts of their network. And they came to us and said, oh, we have this new QKD system from a vendor that we want to try. So we want to take your thing out and put the QKD in. And we said, well, if you do that, you have to take your network down and implement this. And they said, oh, we don't want to do that. We said, or we'll integrate it with ours and your network will stay up as we put this new technology in. And that's what we did. So we actually integrated that technology into our solution, and we just hand the keys to the endpoints. And so that's the idea, is that the technology layer needs to be abstracted from the key delivery layer. And that's what we offer. So we think no matter what the technology is, even if you're teleporting qubits, you're going to need a way to get those to the endpoints without being disruptive. So this is sort of like putting internet wiring, network wiring in a building. I don't know if you're using IPX or TCP/IP or V4 or V6. I just know you need to connect things. And so the wiring, this is sort of the wiring, the foundational infrastructure for key delivery. We think this is provided here.
Fantastic. So we are talking Star Trek, we are talking teleportation, we are talking things that are very much sci-fi. Now that begs a question from me. Does this mean that this technology, this solution, and this approach will apply only to a certain type of companies or certain type of industries? Are there any limitations into the type of organizations that must be using it, the size of organizations that must be using it, and thereby just limiting the scope of application of this solution?
So I'd say the limitation is for businesses that don't care about the security or privacy of their data, they're probably not a good customer. But otherwise, it really doesn't have to do with size. It depends. It's really about how much you value your data and the security of it. The cost of this solution and all the security solutions people have offered ever have come down over time. So I would say the target market is sort of at the SMB and SMB and above right now, and so more on the SMB, sort of the mid-sized businesses and above. But certainly we have small customers that are interested in this and are looking to do it. I think for the SMB market, what you'll see is there will be they're tend to get a lot of these security solutions from other providers, like their service provider, the telco. And so we'll see that bound into the telcos where they can offer this as a security layer for their customers. And then at the enterprise level, that's a huge market for us. But the limitation isn't really what you would think it would be. This isn't a super costly implementation that you have to do. In fact, for a few $100s a month, a small business could secure a couple sites and make sure that was safe and flexible and had all the benefits we're talking about. So it doesn't have to be super expensive for anybody.
Fantastic. So size doesn't necessarily matter. And you said for any organization that don't care about data and security, I think there aren't many of those organizations anymore that don't care about data and security. Even supermarkets are dependent on data. Even smallest of corner shops are also becoming victims of cyber attacks. So everybody has access to some form of sensitive information, personally identifiable information that's always transiting from source to destination, one center to another, be it within their organization and architecture or to another organization that they're collaborating with. So it sounds to me like this can pretty much apply to any company out there that has data, and that data is critical for the nature of their business, right? You also mentioned that existing infrastructure can be leveraged. You can build on top of that as opposed to doing everything from the scratch and from the new. So that's, I believe, fantastic, because the current investments that have been made aren't becoming redundant or obsolete. And you talked about the cost not being very heavy. So it's pocket friendly. It makes them have or get the most of what they already have. And then it prepares them to become quantum safe or to build that quantum safe encryption or post-quantum encryption. All of this sounds music to my ears. And I hope that it sounds music to everybody else's ears here as well. Eric, if you were to tell us in a minute or a minute and a half, a full summary of what we talked about in this session and what people can walk away with, what would that be?
Yeah, so a minute and a half is tight, but we'll try. So I think that the message really is that we have a lot of issues with the current way we do network encryption because it's based on a legacy architecture and technology from the 1970s. And that's being compounded by the fact that we're moving to things like cloud and we're encrypting on more endpoints, not just big computer servers, but telephones and laptops. And so we really need to think about not from a technology standpoint, how can we replace RSA with, again, IBM crystals or classic McAleese, and go from a technology standpoint to think about, are we distributing and generating keys properly so that we don't have to deal with this, with some of the issues that are coming up? And how can we address more than just one issue? I want to address more than just the entropy issue. I want to address more than just the fact that quantum is coming. I want to address multiple things. And so if you can do that economically, and you can do it in a way that, in the industry term is sticky, where you put it in and then people keep it and use it and extend on it and it becomes part of the infrastructure, then that's really cost effective, right? It also means that things get done, which is important because we don't tend to change our crypto very often, as evidenced by the fact that we're still using something from the 70s. So I think, to me, that's the important message is, that you need an architecture that allows you to address multiple things at once, and it isn't going to be a throwaway item. And if you look at identity and access management, I think when people first started to centralize user authentication and authorization, there was some concern that, maybe that wasn't going to be sticky. And it turns out it's super sticky, like it's used everywhere. And no one would even think of building an infrastructure that required user authentication and identity and access management without having a centralized infrastructure to do it. You just wouldn't think about it. And we think going forward, that's the way people want to think about key generation and distribution. It needs to be in its own architecture and, to manage and change that architecture.
Fantastic. Thank you so much. That was a little over a minute and a half, but I think that definitely does justice for those extra few seconds taken. Ladies and gentlemen, Eric Hay, the Director of Field Engineering from Quantum Exchange, one of the partners of Spire Solutions. What a fantastic session this has been. You're watching Cyber Nights, arranged or organized by the Saudi Federation for Cybersecurity Programming and Drones. Thank you to SAP CSP and Cyber Nights for inviting Quantum Exchange and Spire Solutions to be part of this series during Ramadan. We wish you all Ramadan Kareem. Once again, we thank you all for participating, and we thank the Saudi Federation for Cybersecurity Programming and Drones.
Naveen, Eric, it was a pleasure having you at Cyber Nights. It was a very enlightening session. For me and the audience, of course, from such an experienced person such as yourself. Thank you for your time, and we hope to see you guys very soon.
Thank you for having us.
Thank you so much. Ramadan Kareem.